Hi everyone! Today, we're going to explore a really fascinating concept in electronics, how negative feedback makes an op-amp integrate. We'll break down the magic behind the integrating op-amp circuit, focusing on the crucial role that negative feedback plays in its operation. This circuit is fundamental for many applications, from signal processing to analog computers, and understanding its core principle is key to advanced electronics. So, let's dive into the details of the op-amp integrator. At its heart, an integrator circuit uses an operational amplifier, an input resistor, and a feedback capacitor. The input signal is applied through the resistor to the inverting input of the op-amp, while the non-inverting input is typically grounded. The capacitor is connected between the op-amp's output and its inverting input. Now, here's where negative feedback becomes absolutely essential. The op-amp is designed with extremely high open-loop gain, meaning even a tiny voltage difference between its inputs would cause the output to swing to its maximum positive or negative limit, known as saturation. Negative feedback prevents this. The feedback capacitor connects the output back to the inverting input. If the output voltage starts to change in one direction, the feedback loop tries to counteract the change at the inverting input. This action creates what we call a virtual short or virtual ground at the inverting input terminal. Because the non-inverting input is grounded, the op-amp's negative feedback mechanism works tirelessly to keep the inverting input at approximately 0 volts, effectively creating a virtual ground. This virtual ground is the linchpin of the integrator's operation. When an input voltage is applied across the input resistor, a current flows into the inverting input node. Since the op-amp's input impedance is incredibly high, virtually no current flows into the op-amp's inverting terminal itself. Instead, because of the virtual ground, this input current has only one path. It must flow directly into the feedback capacitor. The capacitor then begins to charge or discharge based on the direction and magnitude of this current. The fundamental principle of a capacitor is that the rate of change of voltage across it is proportional to the current flowing through it. In other words, the voltage across the capacitor is the integral of the current. Since the current flowing into the capacitor is determined by the input voltage across the resistor, V_N/R_N, the voltage across the capacitor becomes the integral of the input voltage. The op-amp's output voltage is then essentially the negative of the voltage across the feedback capacitor due to the inverting configuration. Therefore, the output voltage is directly proportional to the integral of the input voltage. Without negative feedback, the op-amp would simply saturate, and there would be no controlled current flow into the capacitor to perform the integration. Negative feedback ensures the op-amp operates in its linear region, precisely controlling the output to maintain the virtual ground and allowing the input current to accurately charge the feedback capacitor, thus enabling stable and accurate integration of the input signal. It's this constant balancing act by the negative feedback that makes the op-amp a predictable and useful integrator. Thank you so much for watching and learning about negative feedback in integrating op-amps. If you found this explanation helpful, please give this video a thumbs up and consider subscribing for more electronics insights and tutorials. Your support helps us create more content like this.